Hello everyone. Today we're going to be learning about the difference between two types of ways of arranging a circuit. The two categories of circuits are called series and parallel. Taking circuit components like batteries and bulbs and resistors and arranging them in one of these two ways will help to determine how your circuit is going to behave. This can mean the difference between a well-working machine, like a smartphone or a TV, and just a pile of junk that doesn't really do anything useful. So it's pretty important to know how these two types of circuits work. Now you can see three circuits in front of me. In the top left is a really simple circuit, in the bottom left is a series circuit, and on the right is a parallel circuit. We're going to build up to understanding how these three work in a moment, but first let's give some basic definitions. What is a series circuit? Well, here are two diagrams. On the left is a more photorealistic diagram that would actually look like the circuits you'll build in your physics class. And on the right is a circuit diagram, which is what you would need to sketch on a piece of paper in order to talk about a circuit that you have built. That's the kind of thing you would need to know how to sketch on a test. So both of these are showing the same circuit, and we would call this a series circuit because there is only one possible path for the electrons in the circuit to flow. We have to know what electrons are doing in a circuit in order to understand what's going on. So remember that the mission of an electron is to leave the negative terminal of a battery and then return to the battery on its positive terminal and get sucked back in and start the journey over again. In this case, there is only one path the electrons can take, and that is out of the negative and then moving clockwise through both of the bulbs until it returns to the positive terminal of the battery. A parallel circuit, on the other hand, gives the electrons choice. We would call a circuit parallel if it allows for multiple pathways for electrons to leave the battery and then return to it. So you can see in this diagram that electrons could leave the negative terminal of the battery, move clockwise through the first loop, and pass only through the top bulb before returning back to the cell. But electrons could also choose an alternate path. They could move down the first wire, then skip the first light bulb and jump down to the bottom bulb, pass through that, and then just move up the blue wires until they go back to the cell. Now, anytime you're building or analyzing circuits, the absolute most important thing to keep in mind is something called Ohm's law. This is an equation that unlocks so much information about a circuit that it's important enough that this fun visual is often found on the internet explaining what the formula says. The formula goes, current equals voltage over resistance. In the comic, you can see that amps of current are trying to flow through a wire or through a circuit component, and then the red ohms of resistance are trying to squeeze the wire or squeeze the component and try to make it harder for the amps to flow. The thing that tries to move the amps and push the current through are volts of voltage. So you can think of this equation called Ohm's law, or I equals V over R, as less of a boring arrangement of letters and more of a battle between volts, which try to push electrons through a wire, ohms, which try to restrict the flow and make it hard for electrons to move, and as those two war with each other, the current that we get is the result. So more resistance would mean less current. However, more voltage would mean more current. The last thing to keep in mind about Ohm's law, which makes it so useful, is that it can be used to understand the behavior of an entire circuit, or you can use Ohm's law to talk about just one individual component of a circuit, like one light bulb or one battery. This means that Ohm's law is not only a powerful tool, but also a flexible one, because you can use it in lots of different circumstances within one circuit. Okay, let's dive into our circuit simulator to figure out what's going on inside of these types of circuits. Today I'm using a simulation called the Circuit Construction Kit DC from phet.colorado.edu. I highly recommend you use this simulation in your own studies as you analyze and build circuits in order to get perfectly correct answers for what should be happening in the circuits you build and analyze. This simulation gives perfect results for what should happen in the real world, so it's a really nice study tool. Alright, let's start by analyzing the simple circuit that I made in the top left. Now I'm calling this a simple circuit because it only has one bulb and one electrochemical cell, or battery as I'll refer to it for the rest of the video, just because I like to give that American nomenclature to my American students. So this battery is powering this one bulb. There's not much complexity in the circuit, so I wouldn't categorize this really as series or parallel. If you were getting really technical, I guess you would call this series, because as I close this switch, we can see that there's only one possible path for electrons to flow. But the categorization of series versus parallel is really more useful for when we have a complexity of components, so not super important to call this series yet, but that's technically what it is. All right, so we can see that this cell, or battery, is pushing electrons out of its negative terminal, and then after a while they go through the bulb. You can see them passing through the filament of the bulb here. Then they exit the bulb, come back up the wires, and get it reabsorbed back into the battery. And then they get powered up by the battery, and they do the journey again. So this is how circuits work. Electrons get pushed out of one end of the battery, and they try to find a path to get back. So since this one bulb is the only thing pushing through, we could probably take a couple measurements and see how the bulb is being powered. And the first tool I'm going to use to measure anything in this circuit is called a voltmeter, which measures volts of voltage. A lot of repetition here. So my voltmeter has two wires, and I can move the wires pretty much anywhere I want in the circuit. I need to arrange it in parallel with a component in order to measure what voltage it is putting out or using. So I'm going to take the negative terminal of the voltmeter and put it near the negative terminal of the battery. I'll do the same thing with the positive terminal of the voltmeter and put that near the positive terminal of the battery. That's something to keep in mind, is that terminals need to match up. Negative goes to negative and positive goes to positive. If you get it wrong and you flip them, you can still get a measurement, but as you can see, it's going to be negative or backwards. So if you ever get a negative answer for a measurement, just flip your wires and that should solve that problem. Okay, so I'm reading 10 volts around this battery. If I click on the values button in the simulation, we can see that that's a correct measurement of how many volts this battery is putting out. Now, putting away my voltmeter for a moment, if we look at any of these circuits that I've built, we can see that every battery has 10 volts of voltage to give to the circuit, and we can also see that each light bulb has 20 ohms of resistance. That's like a toughness factor of how difficult it is to move through those batteries. So as we move along, just keep these numbers in mind. Each battery is 10 volts, and each light bulb is 20 ohms. You could probably use Ohm's law at this point to figure out what the current passing through the circuit should be. So take your best guess. What is the current passing through the wires? Let's see if you were correct. I'm going to use a new tool here called an ammeter, which measures electric current. Remember from a previous lesson that current is the flow rate of electrons. You can almost think of it like the speed of the electrons as they move through the wire. Let's figure out if your answer to how much current is there in this wire was correct. And we get 0.50 amps. If you got that right, give yourself a nice pat on the back. So right here, the current is 0.5 amps, but maybe it's a different current flow somewhere else in the circuit. Let me investigate. Let's find out what the current is right here next to the negative terminal of the battery, and it's still 0.5. What is the flow rate next to the bulb? 0.5. What about inside the filament of the bulb? Also 0.5. What about inside the cell? Also 0.5. What about in the switch that I closed? Also 0.5. Okay, so the moral to the story is here, no matter where you measure the current in a series circuit, the flow is always going to be the same amount everywhere. So why is this? Well, you can kind of think of these electrons almost like cars traveling on a road. And if there's a slowdown, like this light bulb, for example, which has 20 ohms of resistance, that's kind of like a slowdown effect for the circuit. Well, when these cars get to the light bulb, they have to slow down, right? And there are electrons behind those electrons, then those guys would have to slow down too. And in fact, all of the electrons in the entire loop would get slowed down by this traffic buildup effect until all of the entire loop has been slowed down to the same slower speed. Now let's see if the speed of the electrons changes if this is an easier bulb to move through. Let's change this 20 ohms to 10 ohms. Now the bulb is twice as easy to move through because I halved its resistance. Let's check the current. Now instead of 0.5, the current is a full 1 amp. The current doubled in this circuit because the resistance became 1/2 as much. If we look at Ohm's law visually, it should make sense that double the resistance should result in half the current. Likewise, half the resistance should give us double the current. So there's all kinds of proportions and fractions going on here with Ohm's law anytime we manipulate these circuits. Okay, just to make everything the same in all three circuits, let's return this back to 20 ohms and let's carry on. So we've just looked at a simple circuit. I'm going to open this switch so that this circuit shuts off, and I'm going to instead point our attention to the bottom left circuit. Here's our first example of a true series circuit because there are multiple components, and if I close the switch, I can see that there is only one possible path for the electrons to leave one end of the battery and return to the other end. Let's grab our voltmeter and let's start taking some measurements. We should recall from earlier that all of these batteries have 10 volts. So let's measure that just to make sure we know how to use our voltmeter. And there we go, 10 volts. I'm going to leave this voltmeter right here. So this cell or battery is giving out 10 volts. Now, what does that actually mean? We didn't talk about the true meaning of this in the previous circuit, so let's address it now. 10 volts is what this battery is not giving to the circuit. That's the voltage that it gives to each electron. Now, that's really important to mention, that the electrons themselves are each being given 10 volts. That's going to become super important right now as we analyze this circuit. Let's see how this 10 volts is used as we go through this circuit right here. I'm going to analyze how many volts this light bulb is using. Ooh, okay, and we're seeing that there are only 5 volts being measured across this bulb. It says from one end of the bulb to the other, the drop in voltage goes from 10 to 5. So there's only 5 volts after we get through this bulb. We started out with 10, and 5 of those volts are being used at this bulb. Let's check out what's happening at the other bulb. Once again, only 5 volts are being mentioned. Let's see how many volts are being used after this bulb, and it's 0. So what's going on here? Well, this 10 volt battery is giving these two bulbs its 10 volts, but as we can see, only 5 volts is being used up at each bulb. If I measure across both of the bulbs to see how much volts is being used in this whole section of the circuit, I can see that all 10 volts appear. So in total, these two bulbs are using 10 volts, but each of them is only using 5 volts. So this is an important rule about circuits to keep in mind going forward, and I'll kind of summarize it for you at the end. But in a series circuit, voltage is shared between the components. So if you're given 10 volts and you're an electron, you've got to use some of those volts at the first resistor or light bulb, and you got to save some of your volts to spend later at the other light bulb. So you can almost think of volts kind of like money. And these electrons are kind of like, I don't know, students leaving school with a couple bucks in their wallet, and they're going to one restaurant and then another restaurant, and they got to save money for both restaurants along the way. So kind of think of that analogy, that might help. All right, so there's our series circuit. Let's take a look at how current works in the series circuit. Let's measure the current right here, and we get 0.25 amps. Now that's interesting because we haven't seen this number yet, and remember all the components on this page are the same as each other. So why don't we get a familiar number like we did earlier? Let's close this circuit and see what the current used to be. It used to be 0.5 amps. So if it was 0.5 amps in this circuit, why is it 0.25 amps in this circuit? I bet you can figure this out. It's because of Ohm's law. Ohm's law says that current equals voltage over resistance. Well, the voltage is the same in these two circuits. Let's click the values button and confirm that. Both circuits are giving 10 volts to each electron, but the total resistance in the circuit is 20 plus another 20. So there's 40 volts in total in this circuit, unlike the previous circuit, which only had 20 ohms. All right, so let's get rid of the values just to clean up the page. And let's just confirm the rule that we learned earlier about current in a series circuit. Let's just confirm that current is in fact the same everywhere. As I move my crosshair around, I'm seeing 0.25 amps everywhere, even inside the filament of the bulbs. And it seems like that theory is confirmed. Current is once again the same everywhere in a series circuit. That's a pretty easy rule to remember. All right, I think we've taken a look at series circuits enough for now. So now let's take a look at this bad Larry over here. Here's our parallel circuit. As I close this switch, we can see that the electrons have two possible paths for flowing. And if we want to look closely at this juncture right there, we can see that this is where the flow splits off from one wire into two. You can even watch the electrons choosing which path they're going to take. Now you might wonder, how do the electrons know which path they want to take? How do they make that decision? Well, electrons don't have brains, so they can't really choose or decide or think anything, but instead they flow kind of like water, where the path of least resistance, or the easiest path, is the one that most of the water is going to take, like a steeper slope down the mountain versus a flatter slope. So in this case, we have once again a 20 ohm resistor in one branch and another 20 ohm resistor in the other branch. Now these two branches have an equal amount of resistance, so neither of them are easier or harder to pass through than the other. So that means the electrons are going to pretty much choose both paths equally. However, watch what happens if I make one of the branches more difficult to move through. Let's change this bulb from 20 ohms to 40 ohms. Let's make it twice as hard to push through. Okay, so I'm going to take my ammeter, my current measuring device, and I'm going to figure out what the current is that's passing through this branch right here. The current is 0.25 amps. Okay, so we'll keep that number in mind. Let's compare that to the current that's passing downward into this wire, and we get 0.5 amps. So we're getting twice as much of the electron flow passing through the bottom branch than we had through the top branch. Why is that? Why do we get more current down here? And specifically, we get double the current. Because notice how this branch has 0.25 amps, and this has 0.5, so that's double the current. Well, you can probably guess that it's because we have half of the resistance. So taking the resistance and doubling it in the top branch, having twice the resistance, that resulted in 1/2 of the current, as in the other branch. So Ohm's law can still be used to understand this circuit's behavior. Okay, so that explains current and how it can split up inside of a parallel circuit. Now we can see that that's a rule. Current splits up inside of a parallel circuit at these branches. Now we can actually see that the current then joins back up after it goes through these bulbs. So let's see that happen. Here's our 0.25 amps in the top branch, and here's our 0.5 amps in the bottom branch. Let's see them join back up right here, and when the wires come back together, now we have 0.75 amps passing upwards through the top of the circuit, through the cell, through the switch, and all the way back down until we get to this branching path again. And then 0.25 goes this way, and 0.5 goes this way. So the current will split up at these parallel junctions and will rejoin back up at the other parallel junctions on the other side. But they won't necessarily split up evenly. So it really depends on how easy or difficult these two branches are. Now, when you first start out, you can assume in your physics problems that all the bulbs and resistors are going to be the same, like they are now, because I just changed these bulbs back to being identical, 20 ohms and 20 ohms. Now that I know everything is equal, let's see how the current splits up with equal branches. All right, the battery is pumping out 1 amp of current, and in this branch I get 0.5 amps of current, so half of it went that way. And in this branch I also get 0.5 amps, so half of the current went this way. So each branch now has 0.5 and 0.5. Let's watch those 0.5 amps join together here and become 1 amp of current. All right, so I think this is probably making sense to you at this point, how current works in a parallel circuit. So now we get to move on to the most challenging rule of all. How does voltage work in a parallel circuit? Let's take my positive terminal of my voltmeter and put it next to the positive terminal of the battery. Let's do the same thing with our negative terminals, negative to negative, and we get 10 volts. This makes sense because you already know that each cell in this circuit, each battery, has 10 volts of voltage. But again, what does that mean? It means that each of these electrons carries with it 10 volts, which it can use to push through the circuit. So let's follow this one electron's path that I've got my cursor over here. Let's figure out which path it's going to take. And it's going to go down. Okay, so that electron's passing down, down, down. And I'm going to speed up the video a little bit. Okay, and right here, remember this electron has 10 volts of voltage that it can use to push through the circuit. Right now it's pushing through this light bulb and it's using up some of the volts in order to do that. So it's pushing through and spending its volts and spending its volts, and by the time it comes out of that light bulb, it now has less than 10 volts because it had to use some of them to push through the circuit. Now, how many volts did it use? Well, that is the question. We can actually notice now that this electron's future is that it's going to go back up this wire, and when it gets to that junction right above it, it's just going to rejoin with the other electrons from the top path, and it's going to return to the battery. So let's see if this electron has any inclination to go through a second bulb, and then I think that can be the end of our analysis following this one electron, and nope, it just goes right back up to the battery. Okay, so the question was, how many volts did that electron use down here? Well, let's measure the difference in voltage from one side of the bulb to the other, and it is 10. So what does this tell us? It tells us that each electron that passes through this bulb is using all 10 of its volts to pass through that bulb. Now, that kind of makes sense because this is the only bulb that those electrons have to pass through. None of the electrons are going to pass through both bulbs. So unlike in the series circuit, where the 10 volts got split up into 5 volts and 5 volts, no sharing is necessary in the parallel circuit. If you're an electron and you get pushed out of a battery, you get to use all of your volts on whatever branch you choose to go to, because you only have to go through that one branch, not both. So that's why measuring 10 volts up here means you would also measure 10 volts right here across this bulb, and you would also measure 10 volts across this bulb. This concept is a little bit counterintuitive because it seems like 10 is becoming 20, as if the 10 volts of the battery are being used here and here. And 10 can't become 20, we know that. But it's not an and here. It's not 10 volts and 10 volts. It's 10 volts or 10 volts. The electrons are making a choice. Do I use my 10 volts in the top row and then return to the battery? Or do I use my 10 volts in the bottom row and then return to the battery? One last thing we can notice now that I've turned all of the circuits on is the difference in brightness between these bulbs. Here's my original circuit. I just called this a simple circuit. And we can notice that there's a certain amount of light coming out of this bulb. And I suppose the length of these yellow lines tell us how bright it is. Let's compare that to the circuit down below, where we had 2 of those bulbs in series. It looks like these bulbs are dimmer. Now, that should kind of make sense why these bulbs are dimmer than the original one, because unlike the first circuit, these guys only have 5 volts to power them. So less voltage being used at each bulb means each bulb is dimmer. Now, what about the parallel circuit? Well, remember, just like the original circuit in the top left, our circuit on the right here gives 10 volts to each branch of the circuit. And on each branch, there's only one bulb. So the bulbs are getting the full 10 voltage of the battery, just like our original bulb did. So that's why the bulbs in the parallel circuit are just as bright as the bulb in the original circuit. Now this is interesting because it seems like the battery is somehow able to supply twice as much power, and that's also a little bit counterintuitive. We think of batteries as having like one set amount of energy they can give out, but let's actually test that theory. Let's take our ammeter and let's see how much current these identical 3 batteries are all giving out. In the original circuit, the current is 0.5 amps. In the series circuit with twice the resistance, it's only 0.25 amps. And in the parallel circuit, it's a full 1 amp. So how are we getting so much current out of this battery? Well, remember it has 2 branches that it needs to power. So what this tells us is that a battery can actually work harder if it needs to in order to power multiple branches of a circuit. It can either emit low currents when it's hooked up to many things in series, or it can emit medium amounts of current, or it can emit high amounts of current. And the higher currents will happen when you have many branches you're trying to power. This is why it's possible to blow a fuse in your house if you're using too many devices at once, because every time you plug an electronic device into the wall, you're actually adding an additional parallel branch. So that requires more and more current to pass through your circuitry in your house, and that's why the current can get high enough to blow a fuse. All right, now that we've done some exploration into circuits, let's really nail down the 4 rules of circuits and how they work, depending on if you're working with a series circuit or a parallel circuit. The first thing I'll give you is the 2 rules for how voltage works in series and parallel. Here's the rule for series. The voltage of a battery will always be shared between the resistors if those resistors are arranged in series with each other. You can see this happening in the diagram on the bottom, and there's a little bit of an analogy here being made where electrons are kind of like the trucks that are traveling along this road, and what they're hauling is volts of voltage. So the battery sends out each electron with 6 volts to use. 3 of those volts are used up at the first light bulb, and there are 3 left. And then those remaining 3 volts are used up at the second light bulb. As the electrons return to the battery, they have 0 volts left, but then when they go through the battery, they pick up 6 more volts and continue their journey. Since each of the light bulbs only used 3 of the 6 volts, we can see that the voltage of the battery is being shared. All right, here's the rule for parallel circuits. In the same analogy, we have our trucks or electrons picking up 6 volts every time they move through the battery, and then the electrons or trucks decide which branching path they're going to take. The trucks in the bottom path drop off all 6 volts at that first light bulb, and the trucks that take the top path also drop off all of their 6 volts at that light bulb. There's only one bulb they need to pass through, so they never need to share their voltage. So the rule is, voltage is given in full to each parallel branch of a circuit. All right, on this page we're going to talk about how current works in a series or parallel circuit. The first rule for current is how does current work in a series circuit? This is actually the easiest rule out of all the four I'm going to give you because it's just the same number everywhere. So the rule is when resistors are arranged in series, the current is the same everywhere in the loop. We can see there's an ammeter, kind of like the cross arrows moving around in the simulation. The ammeter is moving around the circuit trying to measure what the current flow is everywhere. They go through all the resistors or light bulbs, they even go through the battery or cell, and everywhere they're measuring the same number, which in this case is 2 amps of current. So that's the rule for how current works in a series circuit. It's just the same number everywhere. Here's the rule for parallel circuits and how current works in those. This is pretty complicated by comparison. The rule goes, when resistors are arranged in parallel, the current gets split up at each junction. We can see that happening here, where the current goes from the full 2 amps of current, and it splits into 1 amp and 1 amp, and then even further on in the circuit, one of those units of 1 amp of flow splits again into 0.5 and 0.5. Now, this is not an indication of how current will always split up. It's definitely true that the current will split up at each junction, but the numbers that we'll see will be different each time, depending on how many resistors are on each circuit and how powerful or tough those resistors are. All right, now that you've learned the 4 basic rules of series and parallel circuits and how current and resistance work in each of them, you're pretty well equipped to start building and analyzing circuits yourself. I wish you luck in your future exploration of circuits, and I'll see you in the next video.